Hey everyone, this is Matt with Learn Everything About Design, and in today's video, we're going to talk about designing 3D printed gears in Fusion. So we're going to look at three different styles: the straight Spur Gear style. We're also going to be creating a helical gear pair. So we'll talk about the way in which we can model these. And we're also going to be making a herringbone style, which is going to be basically like two helical gears. And we're going to 3D print all of these. We're going to talk about the way in which we can model them, some of the differences that you can come up with. And we'll also look a little bit about the specifics of the gear and how we can make them actually work as 3D printed gears. So if you want to follow along, we're going to get started by creating a new design. And we want to first create a new component called base plate. Now, this is just simply going to be a component that we use to put the gears on to test them, but I want to keep this at the top of the browser. So I'm going to call this base plate. I'm not going to build anything just yet, and I'm going to disable the activate option just so I have it here. Now, by default, Fusion has changed it so that this is ground to parent. If you don't like that option, you can always go into your preferences and you can go to your design assemblies and you can turn off the first component grounded to parent. I unfortunately leave it on just because in videos it happens to people. So since it's an option, I leave it on. But you can always right click and unground it from parent if you want. In this case, it's going to work fine for us. But in general, I like to turn that off if I could. So the next thing that we're going to do is we're actually going to cheat a little bit. So in the utilities, under the add-ins for scripts and add-ins in Fusion, at the very bottom, one of the original creators of API inside of Fusion included this Spur Gear script in both C and in the Python script language. We're going to run the Python one. It doesn't really matter which one you run. But on the right-hand side, we now have a dialog that gives us all the different parameters that help us define a straight Spur Gear. Now, a straight Spur Gear is going to be probably the simple, straightforward one that we can use, but we need to understand some of these values. So we've got pressure angle, and we've got our module value. The number of teeth is pretty straightforward. Backlash value, root fillet radius, the gear thickness, and the hole diameter. So the module value is actually a calculated value. It's a size ratio based on the pitch diameter and the number of teeth. So for our example, I'm going to be printing some relatively small gears, probably the smallest that you would want to print. So I'm going to use a module of 1. And with 24 teeth, note that this makes our pitch diameter 24. What this means is that when we've got two gears that need to mesh together, they are going to have a 24 millimeter diameter where they're going to be tangent or where they're going to intersect. So we could put the center location of those gears at 48 millimeters apart, and then they would work fine. Now, we are going to adjust or offset that slightly because we are 3D printing and things don't always work out at perfect size. It's not like we're machining parts here. So we want to consider what that really means. The backlash value here, we can also play around with this and add some backlash, which will increase the slop or the gap between these. Now, for the purposes of our 3D printed parts, I'm actually going to leave the backlash at 0. And I'm going to offset the center position or the holes where the center of the gears are going to rotate. I'm going to offset those values by 0.2 millimeters for each of those. So essentially, I'm going to leave the backlash to make a very tight gear. But if you are going to be 3D printing and let's say driving these with motors, then you likely want to play around with this and figure out what works best for you. Now, I've printed a couple of these gears at this size, and I found that leaving the backlash at 0 works out okay. But we do need to sort of tweak some of these other values. The root fillet radius, need to make this fairly small. I'm going to make it 0.2. I wouldn't go any smaller than that for 3D printing, and even 0.2 is relatively small. But we don't want to leave the root of the gear square because it's not going to be as strong. It's going to be a weak point for us. So we want to make sure there's at least some rounded corner there. The gear thickness, I'm going to make all these 10 millimeters tall. We are going to have to play around with some of these other values and parameters when we start to create like our helical and our herringbone gears. But for the most part, this is going to just spit out a straight Spur Gear for us. So once we're done, we'll say, okay, the script is going to run. And now we've got a gear that's a component. When we take a look at this, and we zoom in, this is going to be our root fillet here. And again, we don't really want to leave that square because that's going to be a sharp corner, and we typically call that a stress riser, which means that if you are using this as a true gear, when it starts to push against this tooth, for example, along this direction, what's going to happen is that area is going to be weaker. So we want to leave those fillets there. So with the straight cut gear, all we really need is two of these things. So I'm going to just do Control C and Control V. And when you're working with assemblies, this means that this is the first instance and the second instance. They're exact copies. If I edit one, it's going to edit the other one. So for example, if I go back to my solid tools and say I add a chamfer to this one, it's going to add it to the other one because they're exact copies. Now, if you don't want that to happen, you can right click and use Paste New. Paste New is going to create a unique copy, carry all the features that were used to create that, but it won't be linked to the original. And we're going to do that when we have to go ahead and create our helical gear because we're going to have to make a mirrored pair. So let's go ahead and now let's just create our base plate. And I'm going to start by creating a sketch on this top plane. Make sure that we're selecting the top plane and not the gear itself. And what I want to do is create a line and dimension this line. This is going to be the distance between my two gears. And playing around with this distance is what's going to give us a little bit of space between the gears. Then I'll use my midpoint relationship between that and the origin. I'm going to create a center point rectangle. And this is basically going to be a little holder that we can use. I'll make it 100 millimeters by 50. 50 is probably a bit big. Let's make it smaller than that. Let's make it 25. All we really need is a place where we can put the gears on and have them rotate around. The next thing that we're going to do is we're going to create a circle. And this is going to be for the 10 millimeter for the gear. And I'm going to make this 9.8, give it a little bit of a gap. We'll create another one over here, and we'll make it equal. And then I also want to double check and make a 24 millimeter diameter and make these constructions, so X on the keyboard. All right, so you can see there's instantly a problem here, and this is why we do this and why we add all these different pieces of information, the circles or the dimensions. 48 is too far apart for these gears, and simply because 24 is the diameter, and really what we need is the radius. So this is actually going to be 24 millimeters, which is going to put them directly together. And what this is telling me is that the pitch diameter for these gears, this is the point at which they intersect. Because we are 3D printing and they're not machined and we didn't incorporate any backlash into these, I'm going to space them out slightly. I'm going to add 0.4 millimeters, which is going to put a little bit of a gap in between. And the main reason for this, again, is because we're 3D printing them, we want to back it off just a little bit. So that way the gears are going to engage a little bit more in the arced section and not get stuck in the root of that gear. The second thing that we want to do is we don't want to print this solid, so I'm just going to add some circles on the inside. I'm going to make them equal. And then I'm going to add a diameter here. Looks like 6 millimeters. So that way we just have a cylinder. All right, let's hide the gears for now and let's extrude this. So I'm going to take this whole thing down -2 millimeters. I'm going to bring my sketch back. And then we'll extrude these up 10 millimeters. It's how tall our gears are. So now if we bring our gears back and we activate the top level component, we've got these two gears that we can place. And what I'm going to do is I'm going to use joints, which is J on the keyboard, bottom here, bottom there. Make sure that the motion is set to revolute. We'll say OK. Right click to repeat, and we'll put this one here and here. We'll say OK. And then I'm going to rotate this and capture its position. And then we'll go to Assemble, Motion Link. And between this revolute joint and this revolute joint, we need to reverse the direction and say OK. Now what should happen now is if I rotate this, it's going to make everything move back and forth. Let's go ahead and go to Inspect and turn on Component Colors. And this is going to help us just identify the differences between them. So now that we've got this, I want to go back to my sketch, right click and show the dimensions. And now I can play around with this 24.4. I'm going to make it 24.2. And once it rebuilds, because of all the joints, it's going to push the gears closer together. If we make it exact, so again, exactly what our this diameter is here, what's going to end up happening is this interaction between these two teeth on the gear, it's going to start to bind up because we don't have any backlash, and in reality, the 3D prints are probably going to be a little bit off from the actual size, and this is what we're trying to avoid. Is we don't want to have it to be a perfect fit, especially when it's just plastic on plastic. So we need to add a little bit of a gap. 0.2 millimeters is probably going to work out okay. It gives us a little bit of leeway where we've got a tiny bit of slot between the two. Keep in mind, we've also got a small gap in the diameters here, so there's going to be a slight gap there as well. But it looks like about 0.2 millimeters difference between those is going to be okay. So we'll revert to that position, and now we've got a set of spur gears that we can 3D print, and we can just use them however we need to. But just straight spur gears are not always going to be the best choice. Sometimes you might need something a little bit better at handling load. So what we're going to do now is we're going to take a look at creating a couple of more gears. So let's hide all these components, go back to our utilities, go back to our add-ins, all the way down to our spur gear. And we're going to use all the same settings. So what we're going to do is we're going to kind of fake it a little bit. We're going to say, okay, to create this new gear, this new one, what I'm going to do is I'm going to call this one my Helical Gear 1. And this is because we have to make a mirrored version of it. We're going to activate it. We're going to go into our bodies and sketches folder. And we don't really need to worry so much about sketch 3. That just gives us our pitch diameter. But what we need to do is we need to loft or sweep from the bottom, and we need to go up and twist. So what we're going to do is create a sketch that is going to be on either the front or the right plane. We're going to create a vertical line. That's going to be the height of our gear, in this case 10 millimeters. And then we're going to go to our sweep tool. We'll sweep this bottom profile, and we'll sweep it along this straight line. And then we can define how much twist or angle we want. So in this case, 15 degrees. And we'll say, let's make this as a new body. So the original body we don't need, we'll right click and remove. And now we've got this sort of twisted helical gear. Now, the way that helical gears work is we need an opposing gear for this to work. It has to be twisted the other direction. We can't just flip this one over like we could with a Spur Gear or even the Herringbone Gear. So what we want to do, go back to the top and activate it. We're going to right click on our helical gear and copy it. And then we're going to right click at the top and select Paste New. When we do a Paste New, and just for the purposes of this, I'm going to go ahead and just drag it off to the side, capture the position. But when we do a Paste New, remember that this is a copy that is independent. So with our original Spur Gears, they're both green because they're identical copies. So when we use things like component color cycling. However, with the Helical Gear, the first one is like a dirty orange-brown color, and the second one is blue. Now all we really need to do is activate this one, edit our sweep, and instead of 15, we're going to do minus 15 degrees. So it's going to sweep the other direction. So now what we have, if we activate the top level, is we've got these opposing gears, and that's exactly what we need for this to work. I am going to rename this second one here. Instead of Gear 1, we're going to call it Gear 2. And now we want to bring back our base plate, and we'll go ahead and add these with joints. So J on the keyboard, go ahead and add this one here. Revolute, right click to repeat, add this one down here. Revolute, and again at the top, I'm going to rotate one until they line up. And really the main reason I'm doing this is just so we can visualize it. It's not really required that we put them on a base plate and add these joints, but again, it can be helpful for visualization, especially if you're designing some sort of big component inside of Fusion and you want to see all the motion. We're just going to link the Revolute joints, again, reverse them. And now as we rotate this, we can kind of take a look at what's going on. Now, one thing that you might want to do is go to Inspect and Section Analysis and actually do a section analysis down through the part. just to make sure that the teeth are meshing properly. Again, not required, but it can be helpful to just make sure that everything's working okay. Okay, so now we've got our helical gears, we've got our spur gears, and we've got our base plate. Then the last thing that we want to do is build the herringbone gear. So the way that we're going to do this is I'm going to hide this second helical gear, hide the base plate again, and I'm going to copy this one more time. So we're going to select copy, and we're going to right click and select paste new. So independent copy of it. Make sure that we're not, taking anything from that original gear. And now what we have to do is we need to take this down from 10 millimeters to 5 millimeters, and then we need to go ahead and make a mirrored version of it. So we're going to activate this. We're going to edit the sketch, which controlled the original sweep, and we're going to make that 5 millimeters tall. One of the downsides to this is that it's still going to sweep that 15 degrees over the 5 millimeters instead of doing it over 10 millimeters, which means we've got a little bit more of an aggressive angle here. If you want to fix that, just edit the feature and make it 7.5, and that will give us basically the same sweep that we're using on our helical gear. So we're not making it more aggressive. But again, it really depends on what you're using the gears for. Now that we have this, all we need to do is mirror it. So we're going to go to mirror this body on the top, join them together, and say okay. And as simple as that. Now I'm going to leave it sharp between these two. Honestly, for a 3D printed gear, it's not really going to matter too much because the geometry is going to be the same between both pairs. If you were trying to create a gear like this to machine, then that might be a different story. But for 3D printing, this is a perfectly fine solution. So we're going to copy, we're going to paste, pull it over here, and we'll say okay. And then for this one, because it's in the correct place, all we need to do is an as-built joint for Revolute. We'll select the components, select the position, say okay. And for this one, we need to do a joint, so J on the keyboard. Select the bottom of that. We'll say okay. And then we'll do our motion link. And again, between the last two revolutes, reverse, say okay. So once again, now we can play around with this. We can turn the analysis back on. This is always good to just double check, especially with the gear like this, to make sure that they are meshing properly. And what you can see here is they aren't. It's backwards. So we've got these two sort of overlapped. And what this means is I need to flip or reverse this gear here because that overlap means that they're not meshing properly. So we'll revert, turn the analysis off. And what I'm going to do is I'm going to edit this joint. So for my first selection, I'll put it here, and then I'll flip it over. And we'll say okay. Go back to our analysis. And now when I rotate them, they should be meshing properly. So again, section view, do an analysis, make sure that everything is moving properly and meshing properly. And now we've got a set of herringbone gears that we can 3D print. Now, in order to print all of these, if you want to print them individually, you certainly can. If you want to put them all on a single build, you can. It gets a little bit tricky once we have added all of the different joints because now things aren't going to want to move properly. But what we can do is we can temporarily suppress the joints and then we can manually place these. There is an arrange tool that you can use for 2D arrange. It will make a copy of all the components. But I haven't really had great luck with this in a case like these 3D printed gears because they're all in the same location, so they're really hard to select. But you can certainly play around with that if you want. What I'm going to do is I'm going to select all of these joints, right-click, and suppress them, which means that all these gears should be free to move if I do suppress them properly. Let's try that again. Let's suppress this one, and they should change. It should sort of gray out, so you can see we're moving those gears around. That one can move. Suppress. That one can move. So again, this is a little bit of a pain. It's probably easier to save each file out as an STL and bring them all into whatever slicer you want to use. But if you want to do it in Fusion, at least temporarily, then we'll walk through that process. All right, so what I'm going to do is use the Align tool, and I'm going to take the bottom face of this gear and align it with the bottom of that. I'm not capturing the position, not really worried about it. Repeat Align. And one trick that you can do to speed this up, if you use a right-click marking menu, instead of right-clicking and going to OK and then right-clicking to repeat, once you've positioned it, if you just go to the 12 o'clock position to repeat, it'll automatically accept the position. And this is true for any feature. If you're adding fillets or if you're extruding something or whatever the case might be, just go into that 12 o'clock position to repeat will automatically OK the dialog that you're on. And now from here, looking at it from a top-down view, I'm just going to manually move the gears into a position. Now, if you're looking from a top-down view, they shouldn't move at all in Z. So if we rotate this around, kind of see what's going on. And then we can take the entire design and go to Save as Mesh. And what this will allow us to do is push it to our slicer with all of them positioned correctly. Now, I haven't necessarily saved that position, but what I did in this case was just put them where I wanted to, and then I'm just going to put them into the slicer and print them. A couple things to consider at the slicer level is generally when we slice parts, they're going to have some level of infill. We don't generally print parts solid. So if we go down and we take a look at this, let's just focus on one of these. If we do two traces here, you can kind of see that this is potentially going to be a weak area. So for gears like this, especially small ones, I would say that you want to go and add at least another wall loop. And I would also consider changing the infill pattern. Something like triangles, for example, if we slice this, will create a better intersection between the hub and the gears, something that's more in line with the forces and loads. It's not perfect. You can also go and pick other things. So for example, a honeycomb or some sort of cubic infill. But basically what I try to avoid is doing something that is going to just be strong in one direction, because these are obviously spinning. So doing some sort of other pattern that gives you a better connection between the hub and the outside is definitely something to play around with. When I've printed these, what I've done is either used a honeycomb or some sort of triangle, and then they've seemed to be fine. They've seemed to print just fine. In a case like this, of course, you could use gyroid infill, or in this case, the gyroid would give us a pretty strong intersection between those. Now, the whole thing for the base plate and all 6 gears, in this case on like a Hyper PLA, it's currently printing at about an hour and a half. These gears could obviously be shorter. We could play around with the settings to speed that up if we want. But in general, that's probably what I would assume for all these different parts, is about an hour, hour and a half to get them all printed. They are pretty small. So remember the actual connection point or the intersection between the gears is only about an inch diameter. So they're relatively small gears. If you want to go quite a bit bigger, I would definitely increase the number of walls more than 3, because right now 3 is okay for these small gears, but a larger tooth, I would want the teeth to be solid and then have enough walls to start to build out an internal and an external pass on the hubs. But let's go ahead and take a look at the 3D prints, make sure that everything works, and then we will do a little conclusion. So we can see here on the little base plate that everything is fitting fairly tightly. Again, we didn't include any backlash, so the gears mesh together really well. There will be a vertical seam on one tooth at some point, and that is likely going to cause it to hang up a little bit because of how tight it is. If we made the gap between the 2 pivots or the 2 pins in the middle, that likely wouldn't be a problem. But again, that's something that we need to deal with. I wouldn't go with like a randomized Z seam for these. I would still leave the Z seam along one tooth, but overall that works out pretty well. Now, when we take a look at the helical gears, one thing to consider with helical gears is that The contact points, unlike using just a straight spur gear, which has a complete linear contact point, with the helical gear, we actually get the contact spread over a couple of different teeth. So theoretically, they should be able to hold up to a bit more load. The downside is the angle that we used, in our case, like 15 degrees. That is going to end up adding additional load in a different direction. So you would want to make sure that the direction that you're using the gears can handle that extra side load from the, in this case, 15 degrees that we did. If you're using a straight spur gear, that's not really a concern. There's not an additional side load that's being added from the teeth. And this is where the herringbone is kind of a bit more beneficial, because we get the multiple tooth contact points based on the fact that we've got basically two pairs of helical gears. And then because the helical or the herringbone has the opposing angles on the helical gears, it kind of cancels out that additional force. There is still some force that the teeth take, but it's not going to be moving the entire gear up or down one direction. So that's a really nice sort of meshed pair. It should be able to handle pretty good load. And for parts like this, it's going to be a bit more complex in terms of the meshing and the friction that gets added because of multiple points of contact, but it is a much more stable or better connected gear than just the straight spur gear. So there are plenty more gear types that you could create, but these are three of the basic ones that we can create just by simply using the Spur Gear add-on or the script that's added into Fusion. That alone is a pretty nice addition that gives us the ability to quickly and easily build these out without really having to do a bunch of modeling work. If there are different types of gears that you use on a regular basis and you want to share some information, please leave a comment on that below the video. If there's anything else you want to see 3D printing related or design related, please leave a comment. As I mentioned in all the videos, we have tons of different video requests that we're picking through and trying to get through all of them that are possible. But if you do have any comments, we always add them to our list and we get to them as soon as we can. But as always, thanks for watching, and we'll see you in the next one.